So ladies and gentlemen, we are back, and in this video I'm going to go into detail how the contact process works. This is more of an advanced look through, but stick around. I think it's really interesting. So why do they use contact process? Contact process is the main manufacturing method of sulfuric acid, which is one of the most used reactants, acids namely, in the industry, and it is really useful for a lot of things. So there is a high demand of sulfuric acid, so we need to give supply to that big demand. And this is the method that chemistry industry has come up with, and this is the best or up-to-date method that works most economically and best solution. So get to the chase. They start with the pyrite. You may have heard about pyrite. So pyrite is fool's gold, that shiny little metal looks like gold, but it isn't actually. It is ferrous sulfate. They burn it so it reacts with oxygen and thus forming hematite and sulfur dioxide. This is what we need. Obviously pyrite isn't like that clean, so not only sulfur dioxide forms, but like particles are getting airborne, and also there are like contaminants in the pyrite that contaminate the gas mixture that is going through our system. So we are gonna take care of these by this electrical precipitator and the steam chamber and also the washing tower with these like five basically with the purification unit. Like first of all, removing the particles with these three. You can see these little dots. These are like solid layers, but it is porous. So this mainly is they usually use like quartz or something like that that is porous. So as they pump the air or the gas mixture inside, the gas rises through these little pores and through these little holes, heads like shower heads, drizzle down water or sulfuric acid. They react with the gas that arises through these little holes. So after we have removed the dust with the precipitator, the steam chamber and the washing tower, we can go on to dry the solution. Drying the solution is crucial because we need a dry solution, both because it helps us in the actual formation of sulfur trioxide, thus not like removing any heat from the catalyst, and also because we will need it when we react and get the arsenic out of the reaction or the gas mixture. As I said, there are contaminants, and mainly one of them is arsenic, which is like detrimental to the whole process because arsenic is insidious contaminant in the term that it likes to react with vanadium pentoxide, which is the main catalyst in this process, and it binds to it. So it blocks the catalytic process. So it basically, as they say, it poisons the catalytic material. So it makes a catalytic poisoning. So for this reason, we need to remove as much as we can. We cannot remove all, obviously, but we can remove a lot of it. So through these little columns, it is not the best drawn, but whatever. So you can imagine that there is like an air inlet here. It goes up through this. There are like pegged plates and all these things, and this is the ferrous hydroxide that likes to react with the arsenic from the mixture, and this binds the arsenic and lets the sulfur dioxide go pass and go forward in this in the process. So you can guess that there is some device that allows like little cups that allow this gas mixture rise through this little pocket. In the pocket the gases go through this jelly like or some beads like ferrous hydroxide, and then it does this again and again and again, and it goes out and into the test box, obviously, where they test it for like purity and for contaminations and all this stuff, then into the preheater and into the or contact chamber. So the preheater is there for a reason, because one, we want to preheat the air so it doesn't cool off our lovely vanadium pentoxide. So for this reason, they fire up the vanadium pentoxide first, so they heat it up. Then they heat the preheater. Then they let the whole system run basically. So they pump the gas mixture through. When it gets there, the air is preheated, as I said, and then it comes to the vanadium pentoxide, air plus sulfur dioxide, and also the other stuff that remains. So the sulfur dioxide reacts on the vanadium pentoxide, which is the catalyst, in the excess of oxygen and forms two parts of sulfur trioxide and vanadium quadroxide. This happens at 450 C or 500 C at 1 to 2 atmospheres or 1 to 2 bars basically. So after that happens, because this is a exothermic reaction, it is self-sufficient enough, meaning that it doesn't need any energy from the outside after a point to run. So when it is up to heat, the whole system will heat itself up so much that it will react. Maybe they will need minimal energy to heat, let's say the preheater, or if something is happening, obviously they can heat it, but the generated heat from the absorber tower and the chamber will be enough to preheat the preheater and also keep the reaction going. As we have reacted, other reaction that is happening, as I said, catalytic reaction is taking place. Vanadium quadroxide is reacting with the excess oxygen that's inside this chamber and forms pentoxide again. So it regenerates itself, and this is why it is a catalytic reaction. With this, we can achieve a 95% conversion of all the sulfur dioxide. Unfortunately, 5% or roughly 5% of the sulfur dioxide doesn't react through this catalytic reaction, and that goes through the lid and into the absorption tower with the sulfur trioxide. The sulfur trioxide and the dioxide rises through again these pores, and the washer head just drizzles concentrated sulfuric acid onto it. The concentrated sulfuric acid likes to react with the sulfur trioxide, but it doesn't like to react with the sulfur dioxide. So the sulfur trioxide gets trapped and solved into liquid and forms oleum, that is disulfuric acid or pyrosulfuric acid or whatever they call it. As the acid is drizzling down, the oleum is getting stored in the bottom of the tank, and when it enough is collected, then they tap it down, and then they later water it up, or maybe even water it up with a like a pipe, so it is like a continuous stream, and they pump water into the flowing volume, and they create a constant flow of sulfuric acid. And the heat from this also is recycled and used in the preheater and also in the catalytic chamber if something is going right off. I have said that there is remaining sulfur dioxide that doesn't react. So what do we do with that? Escapes with the waste gases. They usually have more towers, so that is a double contact, double absorption tower system that you can imagine that there is another one of this contact chamber preheater combo. And so basically the 4, 5, and 6 are duplicated. So the waste gases come into another preheater, another contact process chamber, and another absorption tower, meaning that they replicate same effect as I have already told. So with this, they can achieve 99% of efficiency and 99% of all the sulfur dioxide converted into sulfuric acid actually. They used to use platinum for the catalytic reaction as a catalyst, but platinum had some major issues consisting of its price first of all, but also it works on higher temperatures, like almost or even 2 times this temperature, so at like 800 900 degrees Celsius, and at like higher and elevated pressures. So the vanadium, because it is cheap, it is more efficient, and also it is easier to work with, is chosen and more desirable in this process. On my channel, I am making the contact process happen at home, and I am researching and testing and studying relentlessly to make this happen. If you didn't know about that, make sure that you check out my channel. I have, I think, like 3 or 4, yeah, 3 videos about it. It is not much yet, but I'm getting there, as I said. So feel free to join the journey. If you found some value in this video, make sure that you like and subscribe. You know, the YouTube bullshit that they say, spam the comments that you boost up the algorithms so more people can find this video useful or something like that. So thank you for watching. Do the hard work, especially when you don't feel like it. Mwah.